Hi, in this module, I'm going to show you how you can take some real-world problems and model them as constraint satisfaction problems. So we'll begin with our first example, LSAT. So LSAT is the standardized test for admission into law school, and it features these logic puzzles. So here's one example of a logic puzzle. So imagine you have three sculptures, A, B, and C, that are to be exhibited in two rooms, one or two of an art gallery. So the exhibition has imposed a certain number of conditions on you. So sculptures A and B cannot be in the same room. Sculptures B and C must be in the same room. And room 2 can hold only one sculpture. So how do you model this as a constraint satisfaction problem? Let's do it via this JavaScript demo. Erase that and start over. So the first thing you want to do when you model is you figure out what the variables are. So looking back here, we want to put the three sculptures in rooms. So let's just define a variable for each of these sculptures. So in this JavaScript demo, I'm going to define a variable A, and the domain of that A is either 1 or 2, depending on what room that sculpture A should be placed in. And I hit step, and I get this variable, and I can mouse over and I can see the domain of that variable. Okay, so now I can do it for the other two sculptures, B and C. And you'll see that now I have three variables, A, B, and C, each of which can take on values 1 or 2. So now let me define the factors. So I'm going to define a factor for each of these three conditions. Usually each condition corresponds to a factor, but as we'll see later, that's not always the case. So the first condition says that sculptures A and B cannot be in the same room. So this naturally is a factor that touches variables A and B. So I'm going to call that factor AB. Its scope is variables A and B. And remember, a factor is a function that takes on an assignment to the variables in that scope, A and B in this case, and it's going to return a non-negative number. In this case, I want it to be that case that A and B are not in the same room, so I'm going to return A not equal to B. Okay, so if I hit enter, that is going to give me this factor, and I can check its table that says 1, 2 is good, 2, 1 is not. 2, 1 is also good, but 1, 1 and 2, 2 are not good. So now I'm going to move on to the second condition. Sculptures B and C must be in the same room. So this is similar, but now applied to B and C. B and C, and they have to be in the same room, so I'm just going to return B equals C. So I'm going to check that that factor does what I want it to do. So it's happy with 1, 1 and 2, 2, which is good. And now what about the final condition? So room 2 can hold only one sculpture. This one's a little bit tricky because it doesn't mention sculptures exactly, it mentions only the room. But here, what it really means is that I have to look at all the sculpture variables. So I'm going to define a factor, let's call it R2, which depends on all the variables here. And I'm going to need to figure out whether room 2 has at most one sculpture. So let's keep a counter, and we're going to go through all the sculptures and see if sculpture A is in room 2. If it is, I'm going to increment the counter. If sculpture B is in room 2, I'm going to increment the counter. If sculpture C is in room 2, I'm going to increment the counter. And now I'm going to return whether the number of sculptures in room 2, which is now n, is at most 1. Okay, so I make that factor, and I can see that this factor is happy if at most one sculpture is in room 2, or 0. Okay, so now I have defined my constraint satisfaction problem or factor graph, set of variables, set of factors. And now if I press step, then it will magically solve the CSP. And here there is one satisfying assignment, which assigns A to room 2, assigns B and C to room 1. Okay, so that's our first example of solving a constraint satisfaction problem. Here is another example from object tracking. So suppose you're trying to build an autonomous driving system. You want to track where objects are, such as cars and pedestrians, so you know where not to drive. So we're going to work with a very simplified setup here. And here the setting is we're going to have a number of discrete time steps, 0, 1, 2, 3, 4. And at each time step, we're going to have a sensor observation that tells us a noisy indicator of the position of a particular object. So maybe at time step 1, I'm going to observe that the object was at 0. And that's time step 2. I get observation of 2, and at time step 3, I'm going to get observation of 2. So the noisy sensors report these positions 0 to 2. And we know that objects can't teleport. So the question is, what trajectory did the object take? Did it do something like this? And actually the sensor readings were correct, or maybe it did something like that, or something completely different. So how do we do this? We're going to set up a object tracking CSP. So let's first define a factor graph. The variables of the factor graph are going to include the position of the object at each time step, 1, 2, or 3. There's 3 time steps. And the domain of each variable is 0, 1, or 2. So the object could be in position 0, 1, or 2. So xi represents the true position of the object at time step I. So now we're going to define a bunch of observation factors, and this is going to be attempting to incorporate the sensor information into the problem. So remember, at time step 1, we observed that the object was 0. Of course, this is noisy, so we don't want to trust it completely. We're going to define an observation factor, O1, that captures this. So O1 is going to be a unary factor that depends only on x1, and it's going to highly favor assigning x1 to 0, which is the actual observation. But if x1 might be at 1, which is a neighboring location, that's going to have a weight of 1. And if the object is too far away, then at 2, then I'm going to say that's disallowed. So whenever you see a 0 weight, a factor returning 0, that's saying that's a veto. Okay, so O2 is similar, but applied to x2. X2 is, remember, the position of the object at time step 2, and it's going to favor x2 being 2 and degrade if it's a 1 away, and forbid it if it's 2 away. X3 is also similar, but applied to x3, which is the object position at time step 3. It's going to favor x3 equal 2, but also going to degrade and forbid if it's too far away. Okay, so we have 3 observation factors that capture the sensor readings. And now we're going to define transition factors, which represent the fact that objects' positions can't change too much, or in other words, objects can't teleport. So here we're going to write this factor a little bit differently. It's going to be a little bit more compact. So we're going to look at the absolute difference between an object at time step I and an object at the next time step I plus 1. And if the object hasn't moved, which means that the difference is 0, I'm going to assign a weight of 2. If it's moved by 1, then I'm going to assign a weight of 1. And if it's moved by 2, I'm going to assign a weight of 0, which is disallowing it. Okay, so this concludes the definition of the constraint satisfaction problem for this simple object tracking example. And if I click on the demo, I'll show, I can see that what the CSP looks like in JavaScript code. I've defined 3 variables, x1, x2, x3. I'm going to define this helper function nearby that returns 2 if A and B are equal, 1 if they're 1 apart, and 0 if they're 2 apart. And then I'm going to define these factors, O1, O2, O3, and T1 and T2. So if I solve this CSP, this will return all the set of non-zero weight assignments, and I'll see the maximum weight assignment is 1, 2, 2. So this is a solution to a CSP. It's assigning x1, 1, x2, 2, and x3, 2. Looking at this picture, it's 1, 2, 2. So we think that the object probably took this path. Okay, so that's the end of this example. So now let's look at a third example, event scheduling. So CSPs are really suited for generally scheduling problems. So here is an example of a simple scheduling problem. So you have a set of events, and that need to be assigned into a number of time slots. So the events are numbered 1 through E, and the time slots are numbered 1 through T. So we have 3 conditions here. The first condition is that each event must be put in exactly 1 time slot. Condition 2 says that each time slot can have at most 1 event, so you can't double book 2 events into 1 time slot. And then condition 3 says that event E is allowed in time slot T only if this pair exists in a set of allowed pairs. So I can visualize A as a set of edges between the events and the time slots. And here is one possible assignment. I assign event 1 to time slot 2, assign event 2 to time slot 1, and assign event 3 to time slot 3. Notice that I can't assign event to time slot 2 because that would violate C3. There's no edge between event 2 and time slot 2. Okay, so how are we going to model this as a CSP? I'm actually going to show you not 1, but 2 possible formulations of the CSP, which goes to show that there's some flexibility, or you can say artistic license in terms of how you decide to formulate problems as CSPs. Okay, so the first formulation is going to be looking at it from the event's perspective. So here I'm going to define a set of variables. For each event E, I'm going to define a variable xe, and the domain of xe is going to be some integer 1 through t. So notice here that right off the bat, I've satisfied condition C1, because in a CSP, every variable has to take on exactly 1 value, and so that means that each event will be put in exactly 1 time slot. So what about C2? Now I have to do something for C2. Notice that C2 is in terms of time slots, but our variables are in terms of events. So if you remember from the LSAT puzzle, that means we implicitly have to define a factor that looks at all possible variables here. So I'm going to define a constraint, which is for on every pair of events. I'm going to make sure that the time slot that event E was assigned is not the same as the time slot that event E prime was assigned. So if I check this for all pairs of events, now I've satisfied C2. I can guarantee that no time slot has 2 events piling onto it. Okay, so now what about C3? So each event must be only allowed in certain time slots. So here, again, I'm going to look at each possible event, and I'm simply going to enforce that whatever time slot event E was assigned, that's denoted XE, that pair is in the set of allowed event time slot pairs. And that's enough to satisfy condition 3. Okay, so that's the first formulation of a CSP. So now let's look at alternative formulation. So now I'm going to look at from the perspective of time slots. So here I'm going to define a variable yt for every possible time slot t. And yt can take on a value which is either one of the possible events or null, which means that no events have been assigned to that time slot. So notice here right off the bat, I've satisfied condition 2 because remember, every variable gets assigned exactly one value, which is either going to be event or no event. So you can't possibly assign 2 events to a time slot. Now we have to deal with condition 1. So how do we deal with it? So here, all variables are in terms of time slots, but condition 1 is in terms of events. So again, we're going to have to define a constraint that touches all the variables. So for every event here, I need to enforce that if I look over all the time slots, that event shows up exactly once. So what this is saying is that this factor looks at all y1 through yt and checks that yt equals y little t equals e for exactly one of the possible t's. So this will check the box for C1. And now C3 is similar to before. So for every time slot, we're going to enforce that either nothing was scheduled at that time slot, or if something were scheduled, that event and that time slot are compatible. Okay, so that concludes the definition of the second formulation. And now one might wonder which one is better. And this is a matter of efficiency, and there's various trade-offs which are discussed more in the notes. Okay, so here is a final example of a CSP, which is going to be a little bit different, and so it'll be kind of interesting. So this is program verification. So everyone writes programs, and you're probably used to the idea of writing unit tests to check whether a program is correct. But just because you program past a bunch of tests doesn't actually guarantee that it's correct, because you're never sure that you covered all the cases. So the idea behind program verification is to prove that your program works for all possible inputs. So let's work through a simple example. Suppose you have this program, foo, which takes in 2 values, x and y, and it computes the following. So it's going to assign x times x to A. It's going to add y times y to A and then assign that to B. And then it's going to subtract this quantity and assign it to C and return C. So the thing I want to prove here is this following specification, that C is greater than or equal to 0 no matter what value x and y take. So here is how I'm going to specify the CSP. I'm going to define a set of variables that corresponds to both the inputs and also the intermediate quantities that are computed along the way, so x, y, a, b, and c. And now I'm going to define a set of constraints corresponding to the program statements, which are going to relate these variables. And so for the first constraint, I'm going to have a equals x squared, which captures what this first statement is doing. I'm going to have b equals a plus y squared, which is going to capture the second program statement, and c equals b minus 2xy, which is going to capture the third program statement. So an important but really subtle note is that equals means 2 things here. So in the Python program, equal is an assignment operator. It says take the right-hand side, compute its value, and then put it in the variable that is on the left-hand side. Whereas in the CSP, equal represents mathematical equality. It's saying whether the left-hand side is equal to the right-hand side. So, remember what this factor, don't be deceived by the looks of this factor, is actually a function that takes in a value of a and a value of x and checks whether a equals x squared. It returns a 1 or a 0. So it's doing checking. Whereas a equals x times x is doing assignment. It's taking x squared and putting it into a. So now there's a final constraint for the specification, and this is also kind of interesting. Note that we wanted to check that c is greater than 0 for all x and y, but we're going to negate that here because CSPs were doing only looking for an existence of a particular assignment. CSPs can't natively check all possible assignments in a sense. So we're going to negate it. So intuitively, what this is doing is looking for a counterexample. It's going to say, hey, can we find a setting of x, y, a, b, and c such that we are able to find c less than or equal to 0? And if we can, that means the specification doesn't hold. There's a counterexample. But if we're not able to find any consistent assignment, if the CSP is not satisfiable, that means the program satisfies the specification. So it's maybe a little bit counterintuitive at first, but we're proving correctness based on the fact that the CSP has no satisfying assignments. So one thing that's really kind of cool and interesting about formulating the program as a CSP and the fact that this mathematical equality is not it's bidirectional is that the CSP can actually reason in no particular order. It can start with this constraint, c less than 0, and it can work backwards. It can look backwards through c, b, and a, or it can look forwards starting with x and y, or it can do it in kind of a more sophisticated order. Whereas if you were only to execute the program, you can only go forwards. So this shows you kind of the flexibility and power of reasoning over programs using a constraint satisfaction problem. Okay, so we've presented a number of examples of real-world problems and show you how to formulate them as a CSP or two. So how do you do it? Well, first step is to decide on the variables and the domains. And you want to check that an assignment to all these variables gives you the result of interest. And then we take a look at all the desiderata, the constraints and the preferences, the wishes, and translate them into a set of factors. And the nice thing about CSPs is that this process is often parallelizable. So if you have a set of desiderata, usually each desideratum translates into a factor or a set of factors. And then at the end of the day, you just throw in all the factors into your CSP. So there are some notes to keep in mind when you're designing constraint satisfaction problems. You should keep the CSP small so that they will be more computationally efficient to solve. So which means either having fewer variables, fewer factors, a smaller number of domains, smaller number of arities. You can't make everything small, and there's various trade-offs. What exactly is the recipe for computation efficiency really depends on the problem. There's no kind of general rule. So this is going to be a little bit of art here. And finally, one just kind of reminder is that when you think about implementing each factor, it is true that each factor is itself a little mini program, but you should really think of it in terms of checking a solution, checking whether assignment to the variables of that factor encompasses is valid rather than trying to compute the solution. So equals is mathematical equality rather than assignment. And this is really important, and it takes a little bit of getting used to because CSPs requires a fundamentally different mindset than normal kind of procedural programming, which is most salient in the kind of program verification example. But hopefully after a bit of practice, you'll get used to how thinking in terms of CSPs, and hopefully it'll become more second nature. All right, so that's the end of this module.